Space feels empty because most of it is. Between planets, between stars, between galaxies, there exists vastly more nothing than anything else. Look up on a clear night, and the darkness dominates, overwhelming the few scattered points of light that manage to pierce through. This emptiness seems obvious, even comforting. A void, after all, should contain no mysteries, no hidden forces, no invisible structures waiting to be discovered. Just pure, simple nothingness stretching in all directions. And yet every assumption about that emptiness dissolves the moment instruments are pointed toward it. The vacuum of space writhes with invisible forces strong enough to tear stars apart. The darkness glows with ancient light that has traveled for billions of years, carrying information about epochs when the universe was unrecognizably different. The distances that appear to separate celestial objects are themselves dynamic, stretching and warping in ways that everyday experience never hints at. That comfortable emptiness, it turns out, is one of the most deceptive illusions the universe offers. The void is not empty, the darkness is not silent, and the space between things holds secrets that challenge every intuitive assumption about how reality should behave. Welcome to Sleep Knowledge. If you find comfort in exploring the quiet vastness and hidden complexity of the cosmos, settle in and let these space facts unfold slowly. And if you feel moved to, share where you are drifting off tonight. It is always warming to know how far these gentle thoughts travel. Tonight's journey moves through space at different scales, from the familiar worlds circling the sun to the unimaginable distances between galaxies, from the behavior of light crossing billions of years to the slow dance of gravity shaping cosmic structure. These are not separate stories. They connect through the same fundamental rules, the same patient processes, the same underlying physics that governs everything from planetary orbits to the expansion of the universe itself. None of this requires urgency. The cosmos has been unfolding for billions of years. It will continue long after these words fade. What matters now is the gentle exploration, the steady accumulation of perspective, the quiet realization that space is far stranger and far richer than everyday experience would suggest. Settle in and let the universe reveal itself slowly. The moon pulls on Earth with enough force to move entire oceans. Twice each day, water rises along coastlines, drawn by lunar gravity. This tidal bulge follows the moon as Earth rotates beneath it, creating the rhythm of high and low tides familiar to anyone who has spent time near the sea. The effect is not subtle. In some locations, the difference between high and low tide exceeds 15 meters. Entire bays empty and refill. Ships that float during high tide rest on exposed mud when the water retreats. The moon's influence is that direct, that measurable, that undeniable. What intuition might not suggest is that Earth pulls back just as hard. Gravity works both ways. The moon does not simply tug on Earth while remaining unaffected. It feels Earth's gravity in return, and that force is much stronger due to Earth's greater mass. This mutual pull keeps the moon in orbit. Without it, the moon would drift away in a straight line, never to return. Gravity does not play favorites. Every object with mass attracts every other object with mass, and the strength of that attraction depends on both masses involved and the distance between them. The moon is not gradually escaping, but it is slowly drifting away. Each year, it recedes from Earth by about 3.8 centimeters. This happens because of tidal friction. As the moon raises tidal bulges in Earth's oceans, Earth's rotation drags those bulges slightly ahead of the moon's position. The gravitational pull of that displaced water tugs on the moon, transferring rotational energy from Earth to the moon's orbit. Over time, this causes Earth's rotation to slow and the moon's orbit to expand. The process is extraordinarily gradual. Human lifetimes are far too short to notice any change. Even recorded history is too brief. But over hundreds of millions of years, the effect accumulates. Fossils of ancient corals preserve growth patterns that suggest Earth's day was shorter in the distant past. Around 400 million years ago, a day lasted roughly 22 hours instead of 24. The moon was closer then, and tides were stronger. The same physics that governs today also governed the ancient oceans, leaving traces in stone that modern instruments can read. This movement has limits. Eventually, Earth's rotation will slow enough that both Earth and Moon become tidally locked to each other, each showing the same face to the other at all times, orbiting in perfect synchrony. At that point, the transfer of energy ceases and the distance stabilizes. This will take billions of years to occur, far longer than the Sun will remain stable. Long before tidal locking completes, the Sun will have exhausted its hydrogen fuel and begun transforming into a red giant, engulfing the inner planets entirely. The Moon's surface preserves a record of impacts stretching back more than 4 billion years. Unlike Earth, where weather, water, and geological activity constantly reshape the surface, the Moon has no atmosphere, no oceans, and very little internal heat. Once a crater forms, it remains. Some of the largest craters visible from Earth were created billions of years ago, during a period known as the Late Heavy Bombardment, when the inner solar system was struck repeatedly by asteroids and comets. These impacts were not gentle. The collisions released energy equivalent to millions of nuclear weapons, vaporizing rock, creating molten seas of melted material, and throwing debris hundreds of kilometers across the lunar surface. The Maria, those dark patches visible to the naked eye, are not seas of water, but plains of ancient lava. After massive impacts fractured the Moon's crust, molten rock from the interior welled up and filled the basins, creating smooth, dark regions that contrast with the brighter, heavily cratered highlands. These lava flows occurred between roughly 3 and 4 billion years ago. Since then, the Moon's interior has cooled and volcanic activity has ceased. What persists is a frozen record, a snapshot of the solar system's violent youth. Astronauts who walked on the Moon during the Apollo missions left footprints that will persist for millions of years. Without wind or rain to erode them, those impressions remain as sharp today as they were in 1969. The same is true for the equipment left behind: lunar rovers, scientific instruments, flags, and discarded gear. All of it sits undisturbed, waiting in the airless silence. The Moon is not just a celestial body. It is a museum, preserving evidence of both cosmic history and human achievement in a vacuum that refuses to forget. The Sun does not burn. Combustion requires oxygen, and the Sun contains no oxygen in its core. What powers the Sun is nuclear fusion, a process in which hydrogen nuclei collide with such force that they merge, forming helium and releasing tremendous amounts of energy. This happens because of the extreme temperature and pressure at the Sun's center, where temperatures exceed 15 million degrees Celsius. Under these conditions, hydrogen nuclei move fast enough to overcome the electromagnetic force that would normally push them apart. When they fuse, a small fraction of their mass converts into energy, following Einstein's equation E=mc². That tiny amount of lost mass, multiplied by the speed of light squared, produces the energy that lights the solar system. Every second, the Sun converts approximately 600 million tons of hydrogen into helium. In doing so, it loses about 4 million tons of mass, entirely transformed into energy. This has been happening for approximately 4.6 billion years, and it will continue for another 5 billion years before the Sun exhausts the hydrogen in its core. The energy released during fusion does not reach the surface immediately. Photons produced in the core scatter through the Sun's dense interior, bouncing between particles in a random walk that can take tens of thousands of years to complete. Only after that long journey do they finally escape into space, traveling at the speed of light toward Earth and beyond. The Sun rotates, but not as a solid body. Because it is made of plasma, different parts rotate at different speeds. The equator completes a full rotation in about 25 days. This differential rotation twists the Sun's magnetic field, creating loops and tangles that emerge at the surface as sunspots, solar flares, and coronal mass ejections. These phenomena are not merely visual. They have real effects on space weather. When those particles reach Earth, they interact with the planet's magnetic field, funneling toward the poles and colliding with atmospheric gases. The result is the aurora borealis and aurora australis, shimmering curtains of light that appear in the night sky at high latitudes. The colors depend on which atmospheric gases are involved. Oxygen produces green and red hues, while nitrogen creates blue and purple tones. The aurora is not a rare event. It occurs regularly, though it is only visible from certain locations under certain conditions. During periods of high solar activity, auroras can be seen farther from the poles, sometimes reaching latitudes where they are normally absent. The Sun's influence extends far beyond the orbit of Neptune. The solar wind, a constant stream of charged particles flowing outward from the Sun, creates a region known as the heliosphere. This bubble of solar influence stretches more than 18 billion kilometers from the Sun, far into the space between stars. The boundary where the solar wind meets the interstellar medium is called the heliopause. NASA's Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. Both spacecraft continue to send back data, though they are now so far away that radio signals take more than 22 hours to travel one way between the spacecraft and Earth. Mercury, the closest planet to the Sun, experiences the most extreme temperature variations in the solar system. During the day, surface temperatures can reach 430 degrees Celsius, hot enough to melt lead. At night, they plummet to minus 180 degrees Celsius. This enormous range exists because Mercury has almost no atmosphere to distribute heat. On Earth, the atmosphere acts as a blanket, moderating temperature differences between day and night. Mercury lacks this protection. Heat absorbed during the day radiates back into space as soon as the Sun sets, and temperatures drop rapidly. Mercury also has one of the most eccentric orbits of any planet. Its distance from the Sun varies by more than 24 million kilometers over the course of each orbit. When closest to the Sun, it moves faster. When farthest, it slows down. This variation in speed, combined with Mercury's slow rotation, creates a strange relationship between its day and its year. One day on Mercury, from sunrise to sunrise, lasts 176 Earth days. Yet Mercury completes an orbit around the Sun in just 88 Earth days. This means that 2 Mercury years pass during a single Mercury day. The Sun rises, moves across the sky, sets, and rises again. But in that time, Mercury has circled the Sun twice. Despite being small and heavily cratered, Mercury has a magnetic field, something that surprised scientists when the Mariner 10 spacecraft first detected it in the 1970s. Planetary magnetic fields are typically generated by motion in a liquid metal core. For a small planet like Mercury, it was assumed that the core would have cooled and solidified long ago, yet the field persists. Data from NASA's Messenger mission, which orbited Mercury from 2011 to 2015, confirmed that the core is indeed partially liquid, though the exact mechanism sustaining the magnetic field remains an area of active research. Venus rotates in the opposite direction from most planets in the solar system, while Earth, Mars, Jupiter, and Saturn all rotate counterclockwise. When viewed from above the North Pole, Venus rotates clockwise. This retrograde rotation is unusual, and its cause is not entirely understood. One possibility is that Venus was struck by a massive object early in its history, an impact powerful enough to flip its rotation. Another possibility involves gravitational interactions with the Sun and tidal forces acting over billions of years. Whatever the cause, the result is that on Venus, the Sun rises in the west and sets in the east. Venus also rotates extremely slowly. A single Venusian day, one complete rotation on its axis, takes 243 Earth days. Yet Venus orbits the Sun in only 225 Earth days. This means a day on Venus is longer than a year on Venus. The combination of slow rotation and thick atmosphere creates unusual conditions. The dense clouds that envelop Venus reflect much of the Sun's light back into space, making Venus the brightest object in Earth's night sky, aside from the Moon. Yet beneath those clouds, the surface is hotter than Mercury's, reaching temperatures around 465 degrees Celsius. This extreme heat is due to a runaway greenhouse effect. Venus's atmosphere is composed of roughly 96% carbon dioxide, with clouds of sulfuric acid drifting high above the surface. Sunlight penetrates the atmosphere and warms the surface. But the thick blanket of carbon dioxide traps the heat, preventing it from escaping back into space. The result is a planet where surface pressure exceeds 90 times that of Earth at sea level, equivalent to being nearly a kilometer underwater on Earth. Lead would not only melt, but would remain liquid, pooling on the ground. Spacecraft that have landed on Venus have survived only minutes before succumbing to the heat and pressure. Despite these harsh conditions, Venus likely had oceans in the distant past. Early in the solar system's history, the Sun was cooler and less luminous. Venus may have been within the habitable zone, the region around a star where liquid water can exist on a planet's surface. Over time, as the Sun grew brighter, temperatures on Venus increased. Water began to evaporate, and once in the atmosphere, it contributed to the greenhouse effect. This process accelerated, creating a feedback loop. More heat caused more evaporation, which trapped more heat, which caused more evaporation. Eventually, all the water was lost, either escaping into space or locked into chemical reactions with surface rocks. What persists is a cautionary example of how planetary climates can shift beyond habitability. Mars once had liquid water on its surface. Evidence for this comes from multiple sources. Images from orbiters show dried riverbeds, deltas, and vast plains that appear to have been shaped by flowing water. The Mars rovers Spirit, Opportunity, and Curiosity have all found rocks that could only have formed in the presence of water. Minerals such as hematite and clay are telltale signs of past water activity. Some features suggest not just brief periods of wetness, but sustained bodies of water that persisted for thousands or even millions of years. What happened to that water is a question that continues to be explored. Mars has ice today, both at the poles and beneath the surface in lower latitudes. NASA's Phoenix lander confirmed the presence of water ice just below the Martian soil in 2008. More recently, the Mars Reconnaissance Orbiter has detected signs of subsurface ice across large regions of the planet. Yet Mars is far too cold for liquid water to exist on the surface under current conditions. The atmosphere is also too thin. With surface pressure less than 1% of Earth's, water would either freeze or evaporate almost instantly. The loss of Mars's atmosphere is tied to the loss of its magnetic field. Unlike Earth, which has a strong global magnetic field generated by its molten outer core, Mars has only localized magnetic fields in certain regions of its crust. These remnants suggest that Mars once had a global field, but it shut down billions of years ago as the planet's interior cooled. Without a magnetic field to protect it, the Martian atmosphere became vulnerable to the solar wind. Charged particles from the Sun gradually stripped away the atmosphere over millions of years, reducing surface pressure and making it impossible for liquid water to remain stable. Mars has the largest volcano in the solar system. Olympus Mons rises roughly 22 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. It is also enormous in diameter, spanning approximately 600 kilometers across. The slopes are gentle, averaging only a few degrees, making Olympus Mons a shield volcano, similar in shape to those found in Hawaii. However, the scale is incomparable. The entire volcanic structure is so large that if you stood on the surface of Mars at its base, the summit would lie beyond the horizon, invisible due to the planet's curvature. Olympus Mons is not the only giant volcano on Mars. Nearby, in a region called Tharsis, 3 other massive shield volcanoes rise from the surface. Together, they form a volcanic plateau that bulges outward, creating a noticeable distortion in the planet's shape. These volcanoes likely formed over billions of years, with repeated eruptions building layer upon layer of solidified lava. Mars lacks tectonic plate movement, so volcanic activity remained concentrated in the same location rather than shifting as it does on Earth. This allowed individual volcanoes to grow to extraordinary sizes. Whether these volcanoes are extinct or merely dormant stays uncertain. No eruptions have been observed, and most scientists believe volcanic activity on Mars ceased hundreds of millions of years ago. However, some recent studies have suggested the possibility of isolated volcanic activity within the past few million years, based on the relatively young appearance of certain lava flows. Definitive evidence stays elusive, but the idea that Mars might still harbour some internal heat and occasional geological activity cannot be entirely ruled out. Jupiter does not have a solid surface. Descending into Jupiter would not mean landing on firm ground, but rather passing through layers of increasingly dense gas, until pressure and temperature become so extreme that matter behaves in unfamiliar ways. The planet is composed primarily of hydrogen and helium, the same elements that make up the Sunday. In fact, if Jupiter had been roughly 80 times more massive, it would have ignited nuclear fusion in its core and become a star instead of a planet. As it stands, Jupiter is the largest planet in the solar system, with a mass more than twice that of all the other planets combined, yet still far too small to sustain fusion. Deep within Jupiter, the pressure becomes so intense that hydrogen is forced into a metallic state. In this form, hydrogen atoms are compressed so tightly that their electrons move freely, allowing the material to conduct electricity like a metal. This metallic hydrogen layer generates Jupiter's powerful magnetic field, the strongest of any planet in the solar system. The field extends millions of kilometers into space, far beyond the orbit of Jupiter's largest moons. Charged particles trapped in this magnetic field create intense radiation belts that would be lethal to unprotected spacecraft and humans alike. Jupiter's Great Red Spot is a storm that has been raging for at least 350 years, possibly much longer. When astronomers first observed it through telescopes in the 1600s, it was already prominent. The storm is larger than Earth, though it has been shrinking over the past century. In the 1800s, it spanned roughly 40,000 kilometers across. Today, it measures closer to 16,000 kilometers. Despite this reduction in size, the storm shows no signs of dissipating entirely. Wind speeds within the Great Red Spot exceed 400 kilometers per hour, and the storm rotates counterclockwise, completing one full rotation every 6 days. The exact mechanism that sustains the Great Red Spot remains under investigation. On Earth, hurricanes draw energy from warm ocean water and dissipate when they move over land or cooler water. Jupiter has no solid surface and no oceans, so the energy source must be different. One possibility is that heat rising from Jupiter's interior fuels the storm. Another is that smaller storms merge with the Great Red Spot, adding energy and helping to sustain it. Observations from NASA's Juno mission, which has been orbiting Jupiter since 2016, continue to provide new data about the storm's structure, depth, and behavior. Jupiter has at least 95 known moons, and more are discovered regularly as observational techniques improve. The 4 largest, known as the Galilean moons in honor of Galileo Galilei, who first observed them in 1610, are Io, Europa, Ganymede, and Callisto. Each is distinct and geologically fascinating. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes constantly resurfacing the Moon. This activity is driven by tidal heating. As Io orbits Jupiter, gravitational forces from both Jupiter and the other Galilean moons stretch and squeeze Io's interior, generating friction and heat. The result is a landscape dominated by volcanic plains, lava lakes, and plumes of sulfur compounds ejected into space. Europa, by contrast, is covered in a smooth shell of water ice. Beneath that ice, evidence strongly suggests the presence of a subsurface ocean, possibly containing more water than all of Earth's oceans combined. The ice shell is crisscrossed with long fractures and ridges, some of which appear to have formed recently in geological terms. Tidal heating also plays a role here, keeping the subsurface water liquid despite Europa's great distance from the Sunday. This has made Europa one of the prime targets in the search for extraterrestrial life. If liquid water exists in contact with a rocky seafloor, chemical reactions similar to those that support life on Earth could potentially occur. Ganymede is the largest moon in the solar system, larger even than the planet Mercury. It is the only moon known to have its own magnetic field, likely generated by a liquid iron core. Ganymede's surface shows both ancient, heavily cratered terrain and younger, grooved regions that suggest geological activity in the past. Like Europa, Ganymede may harbour a subsurface ocean, though buried beneath a much thicker ice shell. Callisto is the most heavily cratered object in the solar system, its surface saturated with impact scars dating back billions of years. Unlike the other Galilean moons, Callisto shows little evidence of internal geological activity. Its surface has remained largely unchanged for most of solar system history, preserving a record of the early bombardment that shaped all the planets and moons. Saturn's rings are not solid. From a distance, they appear as smooth, continuous structures encircling the planet, but they are actually composed of countless individual particles, ranging in size from tiny grains of dust to boulders several meters across. Most of these particles are made of water ice, with small amounts of rocky material mixed in. The rings extend hundreds of thousands of kilometers from Saturn's cloud tops, yet in most places, they are only tens of meters thick. If you were to scale Saturn down to the size of a coin, the rings would be thinner than a sheet of paper. The origin of Saturn's rings remains debated. One possibility is that they are remnants of a moon or comet that was torn apart by Saturn's gravity, either through a collision or by passing too close to the planet and being ripped apart by tidal forces. Another possibility is that the rings are leftover material from the formation of the solar system, particles that never coalesced into a moon. What is clear is that the rings are not permanent. Over time, particles in the rings slowly spiral inward, raining down onto Saturn's atmosphere. Estimates suggest the rings may be relatively young, perhaps only a few 100 million years old, and that they could disappear entirely within another 100 million years. Saturn has over 140 known moons, though many are small and irregularly shaped. The largest, Titan, is the second largest moon in the solar system and the only moon with a thick atmosphere. Titan's atmosphere is denser than Earth's, composed mostly of nitrogen, with traces of methane and other hydrocarbons. The surface pressure on Titan is about 1.5 times that of Earth at sea level. Methane plays a role on Titan similar to that of water on Earth. It exists as a gas in the atmosphere, condenses into clouds, falls as rain, and collects in lakes and seas on the surface. These are not bodies of water, but bodies of liquid methane and ethane. NASA's Cassini mission, which studied Saturn and its moons from 2004 to 2017, revealed that Titan's surface is shaped by processes remarkably similar to those on Earth. Rivers carved by liquid methane flow across the landscape. Wind-driven dunes stretch for hundreds of kilometers. Seasonal weather patterns shift methane from the equator to the poles and back again. Yet the temperature on Titan's surface hovers around -180 degrees Celsius, far too cold for liquid water. Instead, water ice is as hard as rock, and methane takes on the role that water plays on Earth. Beneath Titan's icy crust, there may be another ocean, this one composed of liquid water mixed with ammonia. Evidence for this comes from measurements of Titan's shape and gravitational field. Like Europa and Ganymede, Titan may harbor conditions where liquid water exists in contact with a rocky interior, raising the possibility of chemical processes that could support life, though the environment would be vastly different from anything found on Earth. Uranus rotates on its side. Most planets in the solar system have axes of rotation that are roughly perpendicular to the plane of their orbits. Earth's axis is tilted by about 23.5 degrees, which creates the seasons. Mars has a similar tilt. Jupiter and Saturn are nearly upright. Uranus, however, has an axial tilt of 98 degrees, meaning its poles lie almost in the plane of its orbit. During Uranus's 84-year orbit around the Sun, each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. The cause of this extreme tilt is thought to be a collision early in the solar system's history. A massive impact, possibly involving an object the size of Earth, could have knocked Uranus onto its side. This is not confirmed, but it is the most widely accepted explanation. The tilt has significant effects on Uranus's atmosphere and magnetic field. Unlike other planets where the magnetic field is roughly aligned with the axis of rotation, Uranus's magnetic field is tilted at 59 degrees to its rotational axis and offset from the planet's center. This creates an asymmetric and complex magnetic environment, unlike anything seen elsewhere in the solar system. Uranus is often called an ice giant, a term that distinguishes it from the gas giants Jupiter and Saturn. While Jupiter and Saturn are composed primarily of hydrogen and helium, Uranus and Neptune contain larger proportions of heavier elements, particularly water, methane, and ammonia. These substances exist in high-pressure forms deep within the planet's interiors, not as the familiar ice found on Earth, but as hot, dense fluids. Methane in Uranus's upper atmosphere absorbs red light, giving the planet its distinctive blue-green color. Neptune, the farthest planet from the Sun, is similar in composition and size to Uranus, but exhibits far more dynamic weather. Despite receiving less sunlight than Uranus, Neptune has the fastest winds in the solar system, with speeds exceeding 2,000 kilometers per hour. This is puzzling. Wind on Earth is driven by solar heating, which creates temperature differences that drive atmospheric circulation. Neptune receives only a tiny fraction of the sunlight that Earth does, yet its winds are far stronger. The energy must come from somewhere, and the leading explanation is that Neptune generates significant internal heat, possibly from slow gravitational contraction or residual heat from its formation. When Voyager 2 flew past Neptune in 1989, it observed a large storm system called the Great Dark Spot, similar in some ways to Jupiter's Great Red Spot. Unlike Jupiter's storm, which has persisted for centuries, Neptune's Great Dark Spot had disappeared by the time the Hubble Space Telescope observed Neptune a few years later. New dark spots have appeared since then, suggesting that Neptune's atmosphere is constantly churning, with storms forming, evolving, and dissipating over timescales of years rather than centuries. Neptune has 16 known moons, the largest of which is Triton. It orbits Neptune in the opposite direction from the planet's rotation, a retrograde orbit that suggests Triton did not form alongside Neptune, but was captured from elsewhere in the solar system, possibly from the Kuiper Belt. Triton is also geologically active, with geysers of nitrogen gas erupting from beneath its icy surface. These plumes rise several kilometers into the thin atmosphere before falling back down as frost. Triton's surface is one of the coldest measured in the solar system, with temperatures around -235 degrees Celsius. Despite this, The presence of active geology indicates that internal heat, likely generated by tidal forces from Neptune, keeps some processes active. Beyond Neptune lies the Kuiper Belt, a region of icy bodies extending from roughly 30 to 50 astronomical units from the Sunday. 1 astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometers. The Kuiper Belt is home to countless small objects, remnants from the formation of the solar system that never accumulated into planets. Pluto, once considered the 9th planet, resides in this region. It was reclassified as a dwarf planet in 2006, not because anything about Pluto changed, but because astronomers discovered many other objects of similar size in the same region, making it clear that Pluto is one of many rather than a unique planetary body. Pluto's surface is more varied than expected. When NASA's New Horizons spacecraft flew past in 2015, it revealed mountains made of water ice, plains of frozen nitrogen, and a large heart-shaped region called Tombaugh Regio. Parts of the surface appear young, with few impact craters, suggesting geological activity within the past few million years. How Pluto generates enough internal heat to drive such activity stays uncertain, but tidal interactions with its largest moon, Charon, may play a role. Charon is unusually large relative to Pluto. The two are sometimes referred to as a binary system because their center of mass lies outside Pluto's surface, between the two bodies. Pluto and Charon are tidally locked to each other, meaning they always show the same face to one another as they orbit their common center of mass. This mutual lock is rare. Earth and the Moon are not yet tidally locked, though they will be eventually. Pluto and Charon achieved this state long ago, creating a stable system where both bodies rotate and orbit in perfect synchrony. The solar system does not end with the Kuiper Belt. Beyond it lies the Oort cloud, a vast spherical shell of icy bodies extending halfway to the nearest star. The Oort cloud has never been directly observed. Its existence is inferred from the behavior of long-period comets, those that take hundreds or thousands of years to complete one orbit around the Sunday. These comets originate in the Oort cloud and are occasionally nudged into the inner solar system by gravitational interactions with passing stars or other perturbations. The outer edge of the Oort cloud may reach as far as 100,000 AU from the Sun, roughly 2 light-years. At that distance, the Sun's gravitational influence is weak, but still sufficient to hold these distant objects in orbit. Light from the Sun takes roughly 8 minutes to reach Earth. This means that when you look at the Sun, you see it not as it is now, but as it was 8 minutes ago. Light does not travel instantaneously. It moves at approximately 300,000 kilometers per second, the fastest speed possible in the universe. Even at this tremendous velocity, crossing the distances in space takes time. Sunlight takes about 5.5 hours to reach Pluto. Light from the nearest star beyond the Sun, Proxima Centauri, takes 4.24 years to reach Earth. By the time that light arrives, the star has moved on. The image seen through a telescope is ancient history. This delay creates a fundamental limitation in how the universe can be observed. Everything seen in the night sky is a view into the past. The more distant the object, the further back in time the observation reaches. Galaxies billions of light-years away are seen as they existed billions of years ago, when the universe was younger, hotter, and structured differently. Some of those galaxies may have changed dramatically, or even ceased to exist in the time it took their light to reach Earth. The present state of distant objects remains unknown and unknowable. Stars are not permanent. They form, evolve, and eventually die, though the timescales involved are so vast that individual human lives capture no meaningful fraction of a star's existence. Stars form in clouds of gas and dust called nebulae. When a region within a nebula becomes dense enough, gravity begins to pull material inward. As the cloud collapses, it heats up. Eventually, the core becomes hot and dense enough for nuclear fusion to ignite, and a star is born. The mass of the star determines its fate. Low-mass stars like the Sun will burn steadily for billions of years before exhausting their hydrogen fuel. When that happens, the core contracts and the outer layers expand, transforming the star into a red giant. Eventually, the outer layers drift away. More massive stars live faster and die more violently. They burn through their fuel in only millions of years rather than billions. When fusion ceases, the core collapses catastrophically, triggering a supernova explosion that can briefly outshine an entire galaxy. The core that remains may become a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain on Earth. In the most extreme cases, the core collapses entirely and nothing can stop it. The result is a black hole, a region of space where gravity is so strong that not even light can escape. Black holes are not visible directly, but their presence can be inferred from their effects on nearby matter. Gas falling into a black hole forms a swirling disk called an accretion disk. Friction within this disk heats the gas to millions of degrees, causing it to emit X-rays that can be detected by space-based telescopes. In some cases, jets of high-energy particles are ejected from the poles of the black hole, streaming outward at nearly the speed of light. These jets can extend for thousands of light years, visible across vast distances. At the center of most galaxies, including the Milky Way, lies a supermassive black hole. These objects contain millions, or even billions of times, the mass of the Sunday. The black hole at the center of the Milky Way, known as Sagittarius A*, has a mass roughly 4 million times that of the Sunday. It is about 26,000 light-years from Earth. Stars near the galactic center orbit this black hole at tremendous speeds. Observations of these stars over several decades have allowed astronomers to map their orbits with precision, confirming the black hole's mass and location. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole located at the center of the galaxy M87, about 55 million light-years from Earth. The image shows a bright ring of light surrounding a dark central region. The ring is created by light from the accretion disk being bent and amplified by the black hole's gravity. The dark region in the center is the black hole's shadow. This image required coordinating multiple radio telescopes around the world to create an Earth-sized virtual telescope. The resolution achieved was equivalent to being able to see a grape on the surface of the Moon from Earth. Galaxies are not randomly scattered through space. They cluster together in groups and superclusters, connected by vast filaments of dark matter and separated by enormous voids where almost no galaxies exist. The Milky Way is part of a small group called the Local Group, which includes roughly 80 galaxies. The two largest members are the Milky Way and the Andromeda Galaxy, a spiral galaxy similar in structure to our own, located about 2.5 million light-years away. The Milky Way and Andromeda are moving toward each other. In roughly 4 billion years, they will collide. This sounds dramatic, but galactic collisions are not violent events in the way that term might suggest. Galaxies are mostly empty space. Even though they contain hundreds of billions of stars, the distances between those stars are so vast that direct collisions between individual stars are extremely unlikely. Instead, the two galaxies will pass through each other, their mutual gravity distorting their shapes. Over hundreds of millions of years, they will merge, forming a single, larger, elliptical galaxy. The Sun and Earth will likely survive this process, though their position within the newly formed galaxy may change. The universe is expanding. This does not mean that galaxies are moving through space away from a central point. It means that space itself is stretching, carrying galaxies along with it. The farther apart two galaxies are, the faster the space between them expands. This relationship, known as Hubble's law, was first observed by Edwin Hubble in the 1920s. By measuring the redshift of light from distant galaxies, Hubble showed that nearly all galaxies are moving away from the Milky Way, and the more distant they are, the faster they recede. This expansion implies that the universe was once much smaller and denser. Tracing the expansion backward in time leads to a moment roughly 13.8 billion years ago, when the universe was compressed into an extremely hot, dense state. This is the Big Bang, not an explosion in space, but an expansion of space itself. In the first fractions of a second, the universe expanded exponentially in a process called inflation, smoothing out irregularities and setting the stage for the formation of matter, atoms, stars, and galaxies. Evidence for the Big Bang comes from multiple sources. The cosmic microwave background, a faint glow of radiation that fills the entire sky, is the afterglow of the Big Bang, cooled over billions of years of expansion. It was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who were testing a radio antenna and noticed persistent noise that could not be eliminated. This noise turned out to be radiation from the early universe, slightly warmer in some directions and cooler in others. Those tiny temperature variations correspond to regions of slightly higher and lower density, which eventually grew into galaxies and galaxy clusters. The universe is not just expanding, but accelerating. This discovery, made in the late 1990s by studying distant supernovae, was unexpected. Gravity should slow the expansion over time, pulling galaxies back toward each other. Instead, observations showed that the expansion rate has been increasing for the past several billion years. The cause of this acceleration is attributed to dark energy, a term that describes the effect without explaining what it is. Dark energy appears to make up roughly 68% of the total energy content of the universe, yet its nature remains one of the biggest unsolved problems in physics. Dark matter is another mystery. Observations of galaxies and galaxy clusters show that the visible matter, the stars, gas, and dust that emit or absorb light, accounts for only a small fraction of the total mass. The rest is invisible, detectable only through its gravitational effects. This unseen mass is called dark matter. It does not emit, absorb, or reflect light, making it impossible to observe directly. Its presence is inferred from the way galaxies rotate, the way light bends around galaxy clusters, and the large-scale structure of the universe. Together, dark energy and dark matter make up roughly 95% of the universe. Ordinary matter, the atoms and particles that make up stars, planets, and people, contributes only about 5%. This is a humbling realization. The familiar world, the one made of known particles governed by known forces, is a tiny fraction of what exists. The rest remains hidden, revealing itself only through its influence on the visible. Neutron stars are among the densest objects in the universe. When a massive star explodes in a supernova, the core that remains may be compressed into a sphere only about 20 kilometers across, yet containing more mass than the Sunday. The matter within a neutron star is packed so tightly that protons and electrons merge to form neutrons. Hence the name. A sugar cube-sized amount of neutron star material would weigh roughly 1 billion tons on Earth. Some neutron stars rotate at extraordinary speeds, completing hundreds of rotations per second. These are called pulsars because they emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse. If Earth happens to lie in the path of one of these beams, the neutron star appears to pulse on and off with remarkable regularity. The fastest known pulsar rotates 716 times per second. At this speed, a point on the star's equator is moving at roughly 1/4 the speed of light. The regularity of pulsars is so precise that they can be used as cosmic clocks. Some pulsars have been monitored for decades, and their pulses arrive with timing accuracy comparable to the best atomic clocks on Earth. This stability makes pulsars useful tools for testing theories of gravity and for studying the interstellar medium through which their signals travel. Gravitational waves are ripples in the fabric of space-time itself. They are produced when massive objects accelerate, such as when two black holes or neutron stars spiral inward and merge. As these objects orbit each other, they lose energy by emitting gravitational waves, causing their orbits to shrink. Eventually, they collide, releasing a final burst of energy that travels outward at the speed of light. These waves were predicted by Einstein's general theory of relativity in 1916, but they were not directly detected until 2015. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected the signal from two merging black holes located more than 1 billion light-years away. The waves stretched and compressed space by an amount smaller than the diameter of a proton. Detecting such a tiny distortion required instruments of extraordinary precision. Since that first detection, dozens of gravitational wave events have been observed. Each one provides information about the masses and spins of the merging objects, the distance to the event, and the behavior of matter and space-time under extreme conditions. Gravitational wave astronomy has opened a new way of observing the universe, one that does not rely on light, but on the fundamental structure of space itself. The universe contains more stars than there are grains of sand on all the beaches on Earth. This comparison is often repeated, but remains difficult to fully grasp. Estimates suggest there are roughly 100 to 400 billion stars in the Milky Way alone. The observable universe contains at least 100 billion galaxies, possibly many more. Multiplying these numbers yields a figure on the order of 10 to the 24th power, a number so large that writing it out in full would require more digits than there are words in this script. Most of those stars likely host planets. Observations from NASA's Kepler Space Telescope and other missions have shown that planets are common. Nearly every star surveyed has at least one planet orbiting it, and many have multiple planets. Some of these planets are rocky, like Earth and Mars. Others are gas giants, similar to Jupiter and Saturn. Still others are unlike anything found in the solar system, such as super-Earths, rocky planets larger than Earth, or hot Jupiters, gas giants orbiting so close to their stars that their atmospheres are heated to thousands of degrees. The search for life beyond Earth focuses on planets within the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Water is considered essential for life, as it is known on Earth, though this does not rule out the possibility of life based on entirely different chemistry. Thousands of exoplanets have been discovered in habitable zones, though most are too far away to study in detail. Future telescopes, such as the James Webb Space Telescope, and proposed missions like the Habitable Worlds Observatory, aim to analyze the atmospheres of these planets, searching for gases that might indicate biological activity. The Fermi paradox poses a question. If the universe is so vast and contains so many stars and planets, why has no evidence of extraterrestrial intelligence been found? Several explanations have been proposed. Perhaps intelligent life is extremely rare. Perhaps it arises frequently but does not last long, either self-destructing or being wiped out by natural disasters. Perhaps civilizations exist but choose not to communicate, or communication is happening but in ways that are not recognized. Perhaps the distances are simply too great. Even traveling at the speed of light, crossing the galaxy would take tens of thousands of years, and no current technology comes close to such speeds. The absence of evidence is not evidence of absence. The search continues. Radio telescopes scan the sky for signals that might indicate intelligent transmissions. Researchers analyze data from space missions for anomalies that cannot be explained by known natural processes. The question remains open, neither confirmed nor ruled out. The universe is vast, and the exploration has only just begun. Time behaves differently depending on gravity and motion. This is not a philosophical statement, but a measurable physical fact. Clocks in stronger gravitational fields run slower than those in weaker fields. Clocks moving at high speeds run slower than those at rest. These effects are small in everyday experience, but become significant when precision matters. GPS satellites, for example, orbit Earth at altitudes where gravity is weaker than on the surface and at speeds of several kilometers per second. Both effects influence the rate at which their onboard clocks tick. Without corrections for these relativistic effects, GPS navigation would accumulate errors of several kilometers per day. This relationship between time, gravity, and motion follows from Einstein's general theory of relativity, which describes gravity not as a force, but as a curvature of spacetime. Massive objects like stars and planets warp the fabric of spacetime around them. Smaller objects, including light, follow paths determined by that curvature. The bending of starlight around the Sun, observed during a solar eclipse in 1919, provided one of the first confirmations of general relativity. The effect is small, but measurable. Light passing close to the Sun is deflected by roughly 1.75 arcseconds, an angle equivalent to the width of a human hair viewed from 10 meters away. Black holes represent the extreme limit of this curvature. Near a black hole, space-time is warped so severely that time slows dramatically relative to distant observers. An object falling toward a black hole would appear to an outside observer to slow down as it approaches the event horizon, the boundary beyond which nothing can escape. From the perspective of the falling object, however, time passes normally. This difference in perspective is not an illusion. Both are correct within their respective frames of reference. Time itself is relative, not absolute. The concept of simultaneity also changes. Events that appear to occur at the same time for one observer may occur at different times for another observer, in motion relative to the first. This concerns not a matter of perception or signal delay. It is a fundamental feature of how time and space relate to each other. Two events that are simultaneous in one frame of reference are not simultaneous in another, if the frames are moving relative to each other. There is no universal now, no single moment that applies everywhere in the universe. The past, present, and future depend on the observer's motion and position in a gravitational field. These ideas can feel disorienting. Everyday experience suggests that time flows uniformly, that the present is the same for everyone, and that simultaneity is a simple, objective fact. Relativity shows that these intuitions, while useful at human scales, do not hold at high speeds or in strong gravitational fields. The universe operates according to rules that go beyond everyday familiarity. Yet it remains consistent, predictable, and describable by precise mathematics. The strangeness does not make the universe unreliable. It reveals deeper layers of structure. Space is not empty, even in regions far from any visible matter. Quantum mechanics predicts that empty space is filled with fluctuating energy, brief flashes of particle-antiparticle pairs that appear and disappear too quickly to be directly observed. These virtual particles are not merely theoretical. They produce measurable effects, such as the Casimir effect, where two uncharged metal plates placed close together in a vacuum experience a tiny attractive force due to differences in the quantum fluctuations between the plates and the surrounding space. Dark energy, the mysterious force driving the accelerated expansion of the universe, may be related to this vacuum energy. If the energy of empty space has a non-zero value, it could exert a kind of pressure that pushes space apart. However, calculations based on quantum mechanics predict a vacuum energy that is vastly larger than what is observed, a discrepancy so enormous that it is sometimes called the worst prediction in the history of physics. Reconciling quantum mechanics with general relativity remains one of the deepest unsolved problems in theoretical physics. The edge of the observable universe is not a physical boundary. It is a horizon defined by the finite speed of light and the age of the universe. Light from objects farther than roughly 46 billion light-years away has not had time to reach Earth. This does not mean the universe ends at that distance. It means that anything beyond that distance is, for now, unobservable. The observable universe is expanding as time passes, not because space itself is stretching faster, but because more time allows light from more distant regions to arrive. What lies beyond the observable universe cannot be known through direct observation. The universe could be infinite, extending in all directions, without end. It could be finite but unbounded. It could contain regions with different physical laws, different constants of nature, or different configurations of matter and energy. These possibilities cannot be ruled out, but they also cannot be confirmed. The observable universe is all that current technology and theory allow access to. What lies beyond remains, for the moment, purely speculative. The oldest light in the universe is the cosmic microwave background. This radiation was released around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was opaque, filled with a hot plasma that scattered light continuously. Once atoms formed, light could travel freely. That light has been traveling ever since, stretched by the expansion of the universe from visible wavelengths into the microwave range. Detailed maps of the cosmic microwave background reveal tiny temperature variations, less than 1 part in 100,000. These variations correspond to regions of the early universe that were slightly denser or slightly less dense than average. Over billions of years, gravity amplified these differences, pulling matter together in the denser regions and leaving voids in the less dense regions. The result is the large-scale structure observed today. Galaxies, galaxy clusters, and vast filaments of matter separated by emptiness. The universe is remarkably uniform on the largest scales. Observations of the cosmic microwave background and the distribution of galaxies show that, averaged over distances of hundreds of millions of light-years, the universe looks roughly the same in all directions. This uniformity is puzzling because different regions of the universe appear to have never been in contact with each other, yet they have nearly identical properties. The theory of cosmic inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang, offers one explanation. Inflation would have stretched a small, causally connected region into a much larger one, smoothing out differences and creating the observed uniformity. Inflation is supported by several lines of evidence. It makes predictions about the patterns of temperature fluctuations in the cosmic microwave background, and those predictions match observations well. It also predicts the existence of gravitational waves from the inflationary period, though these have not yet been detected. If found, they would provide strong support for the theory. If not found above certain sensitivity thresholds, it would challenge or rule out specific models of inflation. The first stars in the universe formed approximately 100 to 200 million years after the Big Bang. These stars were made almost entirely of hydrogen and helium, the only elements produced in significant quantities during the Big Bang. They were likely much more massive than the Sun, burning their fuel rapidly and ending their lives in supernova explosions. Those explosions created heavier elements, carbon, oxygen, iron, and others. Subsequent generations of stars formed from gas enriched with these heavier elements, and the process continued, building up the chemical diversity seen today. Every atom in the human body, heavier than hydrogen, was forged in the core of a star, or in the explosion that ended its life. The oxygen in water, the carbon in DNA, the calcium in bones, the iron in blood, all were created billions of years ago in stars that no longer exist. This is not poetic exaggeration. It is scientific fact, confirmed through spectroscopy, nuclear physics, and observations of stellar evolution. The connection between human existence and the life cycle of stars is direct and measurable. In this sense, people are made of stardust, a phrase that carries both metaphorical and literal truth. The James Webb Space Telescope, launched in 2021, is designed to observe the universe in infrared wavelengths. This allows it to peer through dust clouds that obscure visible light and to detect light from the most distant galaxies, whose light has been redshifted into the infrared by the expansion of the universe. Early results have revealed galaxies that existed only a few 100 million years after the Big Bang, far earlier than many models predicted. These observations are reshaping understanding of how quickly galaxies formed and how the first stars influenced the evolution of the universe. Infrared observations also reveal regions of active star formation hidden within dense clouds of gas and dust. The Eagle Nebula, for example, contains towering pillars of gas and dust where new stars are being born. Visible light cannot penetrate these structures, but infrared light passes through, revealing the stars embedded within. The Hubble Space Telescope captured an iconic image of the Eagle Nebula in visible light, showing the pillars as dark silhouettes against a bright background. The James Webb Space Telescope's infrared view shows the same region in a different light, revealing the young stars that Hubble could not see. The universe does not care whether it is understood. It continues to expand, stars continue to form and die, galaxies continue to collide, and the fundamental laws of physics operate as they always have, indifferent to observation or interpretation. This indifference is not cold or hostile. It is simply the nature of physical reality. The universe is not designed for comprehension. It is governed by consistent rules that can be discovered, tested, and refined. But those rules exist, whether or not anyone is present to study them. This persistence of natural law offers a quiet reassurance. The universe is not fragile. It does not depend on human understanding to function. The same gravity that holds the moon in orbit also governs the motion of distant galaxies. The same forces that power the sun also powered the first stars. The processes that shape planets and stars and galaxies have been operating for billions of years and will continue for billions more. Mystery does not undermine this reliability. It enriches it. The universe is not fully understood, and it may never be. New discoveries raise new questions. Each answer reveals deeper layers of complexity. This does not indicate a failure of science. The exploration continues, not because it will someday be complete, but because the process itself reveals structure, pattern, and connection. Understanding grows, not toward a final conclusion, but toward an ever-expanding view. And so space, vast and mostly empty, filled with forces and matter and energy, in configurations that span from the familiar to the unimaginable, continues its slow unfolding. The distances remain immense. The timescales remain incomprehensible. The structures remain far beyond complete human grasp. Yet within that vastness, regularities persist. Light travels, gravity pulls, matter clumps together, and stars shine. The universe behaves in ways that can be studied, measured, and predicted, even when the full picture stays elusive. This is the cosmos as it is. Not simple, not fully known, but consistent. Not designed for comfort, but offering the stability of persistent natural law. Not waiting to be understood before continuing, but unfolding regardless, patient and indifferent, vast and intricate, holding within its expansion the remnants of ancient stars, the light of distant galaxies, and the quiet assurance that the same rules apply everywhere, always, connecting the smallest moon to the largest cluster in a single, unbroken structure. Comets are often described as dirty snowballs, though this understates their complexity. They are composed of water ice mixed with dust, rock, and frozen gases such as carbon dioxide, methane, and ammonia. Most comets spend the majority of their existence in the outer solar system, far from the sun, frozen and inactive. When a comet's orbit brings it closer to the sun, solar radiation begins to warm its surface. Ice sublimates, turning directly from solid to gas without passing through a liquid phase. This gas, along with dust particles, streams away from the comet, forming a glowing coma around the nucleus, and often creating two distinct tails. One tail is made of dust, pushed away from the sun, by the pressure of sunlight itself. This tail curves gently, following the comet's orbital path. The other tail is composed of ionized gas, blown directly away from the sun by the solar wind. This tail always points away from the sun, regardless of the comet's direction of travel. As a result, when a comet moves away from the sun after passing perihelion, its gas tail leads the way, while the dust tail trails behind. The two tails can stretch for millions of kilometers, visible from Earth, even though the comet's nucleus may be only a few kilometers across. Halley's Comet is perhaps the most famous, returning to the inner solar system approximately every 76 years. Its appearances have been recorded for more than 2 millennia, with observations dating back to at least 240 BCE. The comet's predictable return was first calculated by Edmund Halley in 1705, who recognized that comet sightings from 1531, 1607, and 1682 described the same object. He predicted it would return in 1758. Halley did not live to see this confirmation, but the comet appeared as predicted, and it has been named in his honor ever since. Its most recent appearance was in 1986, and it will return again in 2061. Meteor showers occur when Earth passes through the debris trail left behind by a comet. As the comet orbits the Sun, it sheds dust and small, rocky particles. These particles continue to follow the comet's original path, spreading out along the orbit over time. When Earth's orbit intersects this trail, the particles enter the atmosphere at high speeds, typically 50 to 70 kilometers per second. Friction with atmospheric molecules heats the particles until they vaporize, creating brief streaks of light visible from the ground. Most of these particles are no larger than grains of sand. The Perseid meteor shower, one of the most reliable annual displays, is caused by debris from Comet Swift-Tuttle. The shower peaks each year in mid-August, when Earth passes through the densest part of the debris trail. Under ideal conditions, observers can see 60 to 100 meteors per hour. The Geminids, peaking in December, are associated with an object called 3200 Phaethon, which is likely an extinct comet or a rocky asteroid that behaves like a comet. The meteors from any given shower appear to radiate from a specific point in the sky, called the radiant, which is an effect of perspective. In reality, the particles are traveling on parallel paths, but they appear to diverge from a single point due to the observer's viewpoint, similar to how parallel railroad tracks appear to converge in the distance. Asteroids differ from comets primarily in composition. While comets contain significant amounts of ice, asteroids are made mostly of rock and metal. They reside primarily in the asteroid belt, a region between the orbits of Mars and Jupiter, containing millions of objects ranging in size, from boulders to bodies, hundreds of kilometers across. The total mass of all the asteroids in the belt is less than that of the Moon. The belt is not densely packed. Spacecraft traveling through it rarely encounter anything and do not need to dodge obstacles as often depicted in fiction. The largest object in the asteroid belt is Ceres, now classified as a dwarf planet. It is around 940 kilometers in diameter and contains about 1/3 of the total mass of the entire asteroid belt. NASA's Dawn spacecraft orbited Ceres from 2015 to 2018, revealing a surface marked by impact craters, bright spots of exposed salts, and possible cryovolcanoes that erupted salty water instead of molten rock. Evidence suggests that Ceres may harbor a subsurface ocean, making it another candidate in the search for environments that could potentially support life. Not all asteroids remain in the asteroid belt. Gravitational interactions with Jupiter and collisions between asteroids can send objects into orbits that cross Earth's path. These are called near-Earth asteroids, and thousands have been catalogued. Most are small and pose no threat, but larger impacts have occurred in the past and will occur again in the future. The asteroid that struck Earth 66 million years ago, creating the Chicxulub crater in what is now Mexico, is thought to have been about 10 kilometers in diameter. The impact released energy equivalent to billions of nuclear weapons, triggering wildfires, tsunamis, and a prolonged period of darkness as dust and debris blocked sunlight. This event is linked to the mass extinction that ended the reign of the dinosaurs. Efforts to track and catalogue near-Earth asteroids have intensified in recent decades. Surveys using ground-based telescopes and space missions have identified more than 90% of near-Earth asteroids larger than 1 kilometer. Smaller objects are harder to detect, but are discovered regularly. In 2022, NASA deliberately crashed a spacecraft into a small asteroid called Dimorphos as part of the Double Asteroid Redirection Test, or DART. The impact successfully altered the asteroid's orbit, demonstrating that it is possible to deflect an asteroid if one were found to be on a collision course with Earth. The Sun is not stationary. It orbits the center of the Milky Way galaxy, completing one full orbit approximately every 230 million years. This period is sometimes called a galactic year. The Sun travels at a speed of about 220 kilometers per second relative to the galactic center, carrying the planets along with it. Since the Sun formed about 4.6 billion years ago, it has completed about 20 orbits around the galaxy. The solar system's path through the galaxy is not a simple circle. The Milky Way's disk is not perfectly flat, and the Sun oscillates above and below the midplane as it orbits, crossing the galactic plane approximately every 30 million years. Some researchers have speculated that these crossings could influence conditions on Earth, perhaps by altering the flux of cosmic rays or increasing the likelihood of encounters with interstellar clouds. However, no clear correlation between galactic plane crossings and major events in Earth's history has been firmly established. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure with spiral arms extending outward. The Sun is located in one of these arms, known as the Orion Arm or Orion Spur, about 26,000 light-years from the galactic center. From Earth's vantage point, the densest part of the galaxy appears as a bright band stretching across the night sky. This is the Milky Way, as seen edge-on from within. Ancient cultures around the world incorporated this band into their mythologies, interpreting it as a river, a path, or a bridge. The center of the Milky Way is hidden from view in visible light due to dense clouds of dust and gas. Infrared and radio observations can penetrate these clouds, revealing a crowded region filled with stars, gas, and the supermassive black hole, Sagittarius A*. The density of stars near the galactic center is much higher than in the Sun's neighborhood. If Earth were located there, the night sky would be filled with bright stars, and there would be no true darkness. Voyager 1 and Voyager 2, launched in 1977, are the most distant human-made objects. Voyager 1 is currently more than 24 billion kilometers from the Sun, well beyond the heliopause, and traveling through interstellar space. Voyager 2 is slightly closer, but also in interstellar space. Both spacecraft are still operational, though their power supplies are gradually declining. They carry golden records, phonograph-style discs containing sounds and images intended to represent life and culture on Earth. The records include greetings in multiple languages, music from different cultures, natural sounds such as wind and birdsong, and images of people, animals, and landscapes. The likelihood of the records being found by another intelligent species is vanishingly small. Space is vast, and the spacecraft are moving slowly compared to interstellar distances. Even traveling at their current speeds of roughly 17 kilometers per second, the Voyagers will not approach another star for tens of thousands of years. The records are less about communication and more about marking humanity's presence. A statement that says, "However briefly, we were here." Radio signals from Earth have been traveling outward into space since the invention of radio. The first high-power broadcasts capable of reaching interstellar space, date back to the mid-20th century. These signals travel at the speed of light, which means they have now reached stars roughly 70 to 100 light-years away. This expanding bubble of radio noise contains fragments of television broadcasts, military radar, and communication signals, all fading as they spread across greater distances. Any civilization capable of detecting these signals would need extremely sensitive equipment and would be listening at the right frequency, at the right time. The search for extraterrestrial intelligence, known as SETI, monitors radio frequencies for signals that might indicate intelligent transmissions. So far, no confirmed signals have been detected. The most famous candidate, the WOW signal detected in 1977, was a strong, narrowband radio signal that lasted 72 seconds and has never been observed again, despite repeated attempts to find it. Its origin remains unexplained, though natural phenomena have not been ruled out. Interstellar travel, even at speeds far beyond current technology, poses immense challenges. The distances between stars are so vast that conventional propulsion methods would require thousands of years to reach even the nearest neighboring systems. Proposals for interstellar travel include concepts such as light sails pushed by powerful lasers, fusion rockets, and generation ships where multiple generations would live and die during the journey. None of these technologies exist in practical form, and all face obstacles related to energy, materials, and the physical effects of traveling at high fractions of the speed of light. At velocities approaching a significant fraction of light speed, relativistic effects become important. Time dilation means that time passes more slowly for travelers moving at such speeds compared to stationary observers. A journey that takes decades from Earth's perspective might be experienced as only a few years by those on board. This effect is real and measurable, though it has only been tested at much lower speeds, such as those achieved by particles in accelerators or astronauts in orbit. The concept of a light year is simple, but the distances it represents are staggering. 1 light year is the distance light travels in 1 year, roughly 9.46 trillion kilometers. The nearest star system, Alpha Centauri, traveling at the speed of the fastest spacecraft ever built, it would take tens of thousands of years to cover that distance. Even if technology allowed travel at 10% the speed of light, a journey to Alpha Centauri would still take more than 40 years. The scale of the galaxy reinforces this difficulty. The Milky Way is around 100,000 light-years across. Traveling from one side to the other at the speed of light would take 100,000 years. At more realistic speeds, the journey would take millions of years. The observable universe extends billions of light-years in all directions. Most of it will remain forever beyond reach, separated not by physical barriers, but by the vast, empty distances that define the structure of space itself. Planets around other stars, or exoplanets, were first confirmed in the 1990s, though their existence had been theorized for centuries. Detecting them is challenging because planets do not emit their own light and are much smaller and dimmer than the stars they orbit. Early discoveries relied on detecting the wobble a planet induces in its star due to gravitational interaction. As a planet orbits, it tugs on the star, causing the star to move slightly. This motion can be measured through shifts in the star's spectrum, a technique known as the radial velocity method. Another method, the transit method, detects the slight dimming of a star's light when a planet passes in front of it. The amount of dimming reveals the planet's size, and the timing of transits reveals the orbital period. NASA's Kepler Space Telescope used this method to discover thousands of exoplanets, revolutionizing the field. More recent missions, such as the Transiting Exoplanet Survey Satellite, or TESS, continue this work. Some exoplanets orbit very close to their stars, completing an orbit in just a few days. These hot Jupiters are tidally locked, with one side perpetually facing the star and the other in permanent darkness. Temperatures on the day side can exceed 2000 degrees Celsius, hot enough to vaporize metals. Other planets orbit at great distances, taking hundreds or thousands of years to complete a single orbit. Some planets orbit binary star systems, experiencing complex gravitational influences and unusual seasonal patterns. A few exoplanets have been directly imaged, though this is rare. Most planets are too close to their stars and too faint to be seen separately. Direct imaging requires blocking out the star's light using a coronagraph or other technique and detecting the faint reflected light from the planet. The planets imaged so far are mostly large gas giants orbiting far from their stars, where the contrast between star and planet is more favorable. Water has been detected in the atmospheres of several exoplanets. Spectroscopy allows astronomers to analyze the light passing through a planet's atmosphere during a transit, revealing the presence of specific molecules. Water vapor, methane, carbon dioxide, and other compounds have been identified. These detections do not necessarily indicate habitability, as many of these planets are gas giants with no solid surface, but they demonstrate that the building blocks of life, as it is known on Earth, are present elsewhere. The study of exoplanet atmospheres is advancing rapidly. The James Webb Space Telescope has the capability to detect and analyze the atmospheres of smaller, rocky planets, including those in habitable zones. The discovery of biosignatures, such as oxygen, ozone, or methane, in combinations that suggest biological activity, would be among the most significant findings in the history of science. No such detection has been made yet, but the technology to search for these signs now exists. Seasons on Earth are caused by the tilt of the planet's axis, not by changes in distance from the Sunday. Earth's orbit is slightly elliptical, meaning the distance to the Sun varies over the course of a year, but this variation is small and has little effect on temperature. Instead, seasons arise because Earth's axis is tilted at roughly 23.5 degrees relative to the plane of its orbit. When the northern hemisphere is tilted toward the Sun, it receives more direct sunlight, resulting in summer. 6 months later, when the northern hemisphere is tilted away, it receives less direct sunlight, resulting in winter. The southern hemisphere experiences the opposite pattern. Mars has seasons for the same reason, though they are more extreme due to Mars's greater axial tilt and more eccentric orbit. Dust storms on Mars can grow to cover the entire planet, triggered by seasonal temperature changes. Uranus's extreme tilt means its poles can point almost directly at the Sun, creating seasons that last decades and produce unusual atmospheric dynamics. Earth's axial tilt is not fixed. Over a period of roughly 41,000 years, the tilt varies between about 22.1 and 24.5 degrees. This variation, along with changes in the shape of Earth's orbit and the slow wobble of Earth's axis known as precession, affects the distribution of sunlight across the planet's surface. These changes are thought to influence long-term climate patterns, including the timing of ice ages. The Serbian scientist Milutin Milankovic developed a theory in the early 20th century linking these orbital variations to glacial cycles. His work has been largely confirmed by climate data from ice cores and ocean sediments. The Moon stabilizes Earth's axial tilt. Without the Moon's gravitational influence, Earth's axis would wobble more chaotically, leading to dramatic swings in climate over much shorter timescales. This stabilization is thought to have been important for the development of complex life, providing a relatively stable environment over millions of years. Earth's magnetic field is generated by motion in the planet's outer core, a layer of molten iron and nickel located roughly 2,900 kilometers below the surface. The motion is driven by heat escaping from the core and by the rotation of the planet. This creates a dynamo effect, converting kinetic energy into magnetic energy. The field extends tens of thousands of kilometers into space, forming the magnetosphere, which deflects most of the solar wind and protects the atmosphere from being stripped away. The magnetic field is not constant. It weakens and strengthens over time, and the magnetic poles wander. Currently, the North Magnetic Pole is moving across the Canadian Arctic towards Siberia at a rate of several tens of kilometers per year. The field has also reversed many times in Earth's history, with the North and South magnetic poles switching places. These reversals occur irregularly, sometimes millions of years apart, sometimes only tens of thousands of years. The last reversal occurred roughly 780,000 years ago. Evidence for past reversals is preserved in rocks, which record the direction of the magnetic field at the time they solidified. A reversal does not happen suddenly. The process takes thousands of years, during which the magnetic field weakens and becomes more complex, with multiple poles appearing temporarily. During this time, the protection offered by the magnetosphere is reduced, allowing more cosmic rays and solar particles to reach the atmosphere. This could have effects on climate and on the survival of organisms sensitive to radiation, though no mass extinctions have been definitively linked to magnetic reversals. Cosmic rays are high-energy particles, mostly protons, that travel through space at nearly the speed of light. They originate from various sources, including supernova explosions, pulsars, and other energetic events. When cosmic rays strike Earth's atmosphere, they collide with air molecules, creating showers of secondary particles that cascade down toward the surface. Some of these particles reach the ground, and a small number pass through the human body at any given moment. The biological effects of this exposure are minimal under normal circumstances, as Earth's atmosphere and magnetic field provide substantial shielding. At higher altitudes, cosmic ray exposure increases. Passengers on commercial flights receive slightly more radiation than those at sea level, though still well within safe limits. Astronauts on the International Space Station are exposed to higher levels, and those traveling beyond low Earth orbit, such as future missions to the Moon or Mars, will experience even greater exposure. Shielding from cosmic rays is one of the challenges that must be addressed for long-duration space missions. The Sun's activity influences the flux of cosmic rays reaching Earth. During periods of high solar activity, the solar wind is stronger, and it helps deflect some cosmic rays away from the inner solar system. During periods of low solar activity, more cosmic rays reach Earth. This creates a cycle tied to the roughly 11-year solar cycle, during which the number of sunspots and solar flares rises and falls. Sunspots are temporary dark patches on the Sun's surface caused by concentrations of magnetic field lines. These regions are cooler than the surrounding areas, which is why they appear dark. Despite being cooler, they are still extremely hot, with temperatures around 3,800 degrees Celsius compared to the surrounding 5,500 degrees. Sunspots typically appear in pairs or groups and can last from a few days to several weeks. The number of sunspots varies in a regular cycle, with periods of high activity, known as solar maximum, and periods of low activity, known as solar minimum. Solar flares are sudden, intense bursts of radiation from the Sun's surface. Often occurring near sunspots, they release energy across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. When a flare is directed toward Earth, it can disrupt radio communications, interfere with GPS signals, and even damage satellites. Coronal mass ejections, or CMEs, are larger eruptions that send billions of tons of charged particles streaming into space. If a CME reaches Earth, it can compress the magnetosphere, trigger intense auroras, and in extreme cases, induce electric currents in power grids, potentially causing blackouts. The most powerful geomagnetic storm on record occurred in 1859, known as the Carrington event, after the astronomer who observed the solar flare that triggered it. Telegraph systems around the world were disrupted, with some operators receiving electric shocks and telegraph paper catching fire. Auroras were seen as far south as the Caribbean, If a similar event occurred today, the impact on modern technology would be far more severe, affecting satellites, power grids, and communication systems. Space weather forecasting has become an important field, monitoring the sun for signs of flares and CMEs that could affect Earth. Satellites positioned between the Sun and Earth, such as the Solar and Heliospheric Observatory, or SOHO, provide early warning of incoming solar storms, typically 15 to 30 minutes before they reach Earth. This allows time for protective measures, such as shutting down vulnerable systems or reorienting satellites to reduce exposure. The Sun will not shine forever. When this happens, the core will contract and the outer layers will expand, transforming the Sun into a red giant. At this stage, the Sun will swell to a size that may engulf the orbits of Mercury and Venus, and possibly Earth. The outer layers will eventually be ejected into space, forming a planetary nebula, while the core will shrink into a white dwarf, a dense remnant roughly the size of Earth, but with a mass comparable to the Sunday. This white dwarf will gradually cool over trillions of years, fading from white to yellow to red, and eventually becoming a black dwarf, a theoretical object that emits no light. The universe is not old enough for any black dwarfs to exist yet. The first white dwarfs, formed billions of years ago, are still glowing faintly. Planetary nebulae, despite the name, have nothing to do with planets. The term was coined by early astronomers who thought they resembled planets when viewed through small telescopes. In reality, they are shells of gas and dust expelled by dying stars, illuminated by the ultraviolet light from the hot core left behind. These nebulae come in a variety of shapes, from simple spheres to complex structures with rings, jets, and multiple shells. The shapes are influenced by factors such as the star's rotation, magnetic fields, and whether the star had a companion. The heavier elements created in the cores of massive stars and dispersed by supernova explosions are essential for the formation of planets and life. The early universe contained only hydrogen, helium, and trace amounts of lithium. All other elements, from carbon to iron and beyond, were forged in stars. Supernova explosions scatter these elements into space, where they mix with clouds of gas and dust and eventually become part of new stars, planets, and other objects. This means that the atoms making up Earth, the oceans, the atmosphere, and every living thing were once part of stars that exploded billions of years ago. The calcium in bones, the iron in blood, the oxygen in the air, all came from stellar processes. This connection between life and the cosmos is not abstract. It is measurable, traceable through the abundances of elements and the history of the universe. The universe continues to evolve. Stars form and die, galaxies merge, and the expansion of space accelerates. In the distant future, billions of years from now, the accelerated expansion driven by dark energy will carry galaxies farther apart. Eventually, galaxies outside the local group will move beyond the observable horizon, their light redshifted out of detection. The night sky will contain only the merged remnant of the Milky Way and Andromeda, along with a few smaller galaxies surrounded by darkness. Trillions of years from now, star formation will cease as the available gas is used up. Existing stars will burn out and the universe will grow darker. Eventually, only stellar remnants will remain. White dwarfs, neutron stars, and black holes, slowly radiating their remaining energy into the void. Even black holes will not last forever. Quantum effects predict that they will slowly evaporate through a process called Hawking radiation, though this process takes an unimaginably long time. The smallest black holes would take longer than the current age of the universe to evaporate. Supermassive black holes would take 10 to the 100th power years or more. The ultimate fate of the universe depends on the nature of dark energy. If dark energy remains constant, the universe will continue expanding forever, cooling and dimming until it reaches a state, sometimes called heat death, where no usable energy remains and no processes can occur. If dark energy weakens over time, expansion might slow, allowing gravity to pull matter back together in a big crunch. If dark energy strengthens, expansion could accelerate to the point where even atoms are torn apart in a big rip. Current observations suggest the first scenario is most likely, though uncertainties remain. These distant futures are far beyond human timescales. The Sun will die long before the universe reaches any of these endpoints. Humanity, if it survives, will face challenges long before then. From the Sun's increasing luminosity to the eventual exhaustion of resources on Earth. Whether intelligence survives to witness the far future of the cosmos depends on choices made now and in the coming centuries. The universe as it exists today is the result of billions of years of evolution. From a hot, dense beginning to the structured, diverse cosmos, observed through telescopes and measured by instruments, it is a universe that can be studied. A universe that responds to inquiry, with data, patterns, and laws that hold across time and space. This consistency allows prediction and understanding, even as much remains unknown. The mystery does not make the universe unreliable. It makes it deep. Each discovery reveals layers, connections, and questions that lead to further exploration. The process does not diminish wonder, but sustains it. The universe is both knowable and inexhaustible, open to investigation, yet always offering more than can be fully grasped. Space is vast. Time is long. The structures that emerge from fundamental forces and particles are intricate and varied, from the dance of atoms to the slow collision of galaxies. Throughout, the same principles apply. Gravity pulls, light travels, energy transforms, matter clusters and disperses. These are not mysteries in the sense of being unknowable. They are patterns, tested and refined through observation, applied across contexts as different as the orbits of planets and the expansion of the universe. And so, the cosmos persists, indifferent to observation but open to study. It does not pause for comprehension, does not wait for understanding before continuing its unfolding. Stars burn whether anyone watches. Galaxies collide whether anyone calculates their trajectories. The universe is patient, not in the sense of waiting, but in the sense of continuing regardless, offering its phenomena freely to those who look, always more complex than first appearances suggest, always structured by laws that can be learned but never exhausted. And so the cosmos persists, indifferent to observation but open to study. It does not pause for comprehension, does not wait for understanding before continuing its unfolding. Stars burn whether anyone watches. Galaxies collide whether anyone calculates their trajectories. The universe is patient, not in the sense of waiting, but in the sense of continuing regardless, offering its phenomena freely to those who look, always more complex than first appearances suggest, always structured by laws that can be learned but never exhausted. The journey through this vastness is not about reaching an endpoint. It is about moving through layers of understanding, seeing patterns emerge, recognizing connections, and holding the tension between what is known and what remains open. The universe does not demand certainty to function. It operates with or without human comprehension, and in that indifference lies a quiet reassurance. Reality is stable. The laws persist. The exploration continues. Light carries information across distances so vast that the journey itself becomes part of the story. A photon leaving a distant galaxy billions of years ago travels through expanding space, its wavelength stretched by the universe's growth, until it arrives at a telescope mirror and ends its journey. In that moment, past and present connect. The galaxy as it was meets the observer as they are. This is not poetic abstraction, but physical reality. Every observation of distant objects is also an observation of distant times. The speed of light creates a fundamental limit on how quickly information can travel. Nothing can move faster. No signal can be sent, no force transmitted. no influence propagated at speeds exceeding roughly 300,000 kilometers per second. This limit is not imposed by technology or engineering. It is woven into the structure of spacetime itself. Cause and effect depend on it. Without this limit, causality would break down. Events could influence their own causes, and the orderly flow of time would dissolve into paradox. This limit shapes what is observable and what can be known. Events occurring right now on the far side of the universe cannot be detected yet, because their light has not had time to reach Earth. The observable universe is bounded not by a physical edge, but by the time available for light to travel. Beyond that boundary, the universe may continue indefinitely, filled with galaxies and stars, and perhaps other forms of matter and energy, but those regions remain, for now, beyond reach. The concept of now becomes ambiguous over cosmic distances. Two events, separated by billions of light years, cannot be said to occur at the same time in any absolute sense. Simultaneity depends on the observer's frame of reference. Relativity teaches that time is not a universal backdrop against which events unfold. It is part of the dynamic structure of the universe, linked to space and shaped by gravity and motion. This does not indicate a failure of language or measurement. It is the way the universe operates. Yet within this relativistic framework, consistency holds. The laws of physics are the same everywhere. An atom behaves the same way in a distant galaxy as it does in a laboratory on Earth. Light travels at the same speed regardless of location. Gravity follows the same rules. This universality allows astronomers to interpret observations from billions of light years away using principles tested here. The universe does not change its rules depending on location or time. Patterns repeat at different scales. The same gravitational forces that hold the Moon in orbit around Earth also govern the motion of stars around galactic centers and the drift of galaxies through space. The same electromagnetic forces that bind electrons to nuclei also shape the behavior of plasma in stars and the interaction of light with matter. The same quantum mechanics that describes subatomic particles also applies to the behavior of atoms in distant nebulae, where conditions are vastly different, yet the underlying principles remain unchanged. This unity across scales and distances provides a foundation for understanding. The universe is not a collection of disconnected phenomena requiring separate explanations. It is a coherent system governed by a small set of fundamental laws. Those laws interact in complex ways, producing the diversity of structures and behaviors observed, but the foundation remains simple and consistent. And so the exploration of space, whether through telescopes, spacecraft, or mathematical models, reveals not chaos but order, not randomness but pattern, not fragmentation but connection. The same principles that govern the fall of an apple govern the orbit of planets, the formation of galaxies, and the expansion of the universe. Understanding one helps illuminate the others. The cosmos is not opaque. It responds to inquiry. It reveals its structure to those willing to observe carefully and think rigorously. The vastness does not diminish meaning, it deepens it. Every atom in existence shares a history. Every photon, a journey. Every structure, a connection to fundamental forces that have operated since the earliest moments. The universe is not indifferent in a negative sense. It simply continues, offering its patterns, its regularities, its quiet persistence as evidence that beneath the complexity lies coherence. And so, as the night deepens and thoughts slow, the universe remains. Stars still burn in distant spirals, planets still orbit, gravity still pulls, light still travels. The same processes that shaped the cosmos over billions of years continue tonight, tomorrow, and beyond. The exploration is endless, not because understanding is impossible, but because depth is limitless. Each answer opens further questions. This is not frustration, it is richness. The universe offers both what can be known and what remains to be learned. both the familiar patterns of planetary motion and the strange behaviors of distant quasars, both the reassuring stability of physical law and the ongoing mystery of dark energy. All of it persists, connected, coherent, and open to exploration. Better sleep, a lighter day.